Here, once again, we're going to be using an application of the power series. This time we're going to be using the power series to represent a function. And we've done that before, but in this case, we'll need a more complicated process to be able to write this function. And that is because we're going to have to use derivatives to create the function. So the goal is to write this as a series for which we can find the convergence. So in other words, we have to be able to recognize it. It'll likely be the geometric because of the power of k. That is our most common series with the power of k. The k in front, this coefficient of k in front of the x, is implying that we'll need at least the first derivative. K minus 1 would imply the second, and k minus 2 the third, and so on. And that's because as we take the derivative of x to the k will move out in front as a coefficient, and we will take away 1 from the exponent. So the second derivative of x to the k would have a k minus 1 as the coefficients, and then an x to the k minus 2. Since we have the k out in front, we're probably just going to need that first derivative, which also means that we're going to have to adjust this x so that it looks like x to the k minus 1, even though we were given a k plus 3. So moving down and jotting down that example, we have the summation as k goes from 1. Let's make a note of that because it's not starting at 0. So our first term, or our a term, will not be 1 in this case. We'll have to figure out what it is. Negative 1 to the k times x to the k plus 3, all over 6 to the k. Our goal is to write this as a geometric, so it's got to look like some sort of just x to the k case when we're done. X can be really complicated. It can be like negative x over 6, pretty sure that's what it ends up being, to the k. As long as it's just something to the k, it'll be a geometric, and we can use that convergence of a over 1 minus r to be able to find the function. So that's our goal. We're going to take advantage of these two ideas to be able to rewrite this. So I've got to get this negative 1 to the k, this x to the k, and the 6 to the k all together as one fraction that just has a k power, which means I also need to be able to get rid of this coefficient of k because it doesn't fit with the regular geometric series. So let's just group some stuff real quick. Summation k equals 1 to infinity. I'm going to move the k. I'm going to keep the x to the k with it. I'm going to move the other 3 x's away. So that's our x to the k plus 3 is just written separately now as x to the k times x to the 3. I'm going to move over the negative 1 to the k and the 6 to the k because those are pretty much done. I don't have to do anything with those. All right, x to the 3 has nothing to do with our index of k, so it can come outside of the summation. So that's just x to the 3 in front. K is equal to 1 to infinity because, again, this x to the 3 has nothing to do with our counter, so it's just essentially a constant that we can move out front. Now we have to deal with this k times x to the k. We need it to look like this so that we can rewrite it as a derivative. So I'm going to take one of the k's, take one away from the exponent. So this is k times x to the k minus 1 plus 1. I'm going to use that adding 0 trick. Minus 1 plus 1. Rewriting the rest of this. So I'm going to move the plus 1 to go with the 3, and I'm going to take advantage of this to rewrite the derivative, which is d dx of x to the k. All right, so our next line, x cubed times the summation, k equals 1 to infinity. Rewriting this as the derivative, d dx of x to the k. Mushing these two numbers together, we got x to the 4th, and then just rewriting the rest of it, negative 1 to the k over 6 to the k. Now I'm taking a derivative with respect to x. Oops, I have that x in there twice. Sorry. Rewrite those two lines. So I said I was going to move out, but I didn't, x cubed, and that became x 4th, and now on the next line we'll move it out. Okay, so x to the 4th moving that out, k equals 1 to infinity. I have a derivative in terms of x, but these two don't have an x, so there's nothing stopping me from moving it in because they're just constants. So it would be like d dx of 2x is exactly the same as 2 times d dx of x. It doesn't matter if the 2 is inside or outside. So we're going to take advantage of that and move these constants inside so we can start grouping all the k powers together. So that is x to the k, negative 1 also to the k, and 6 to the k. And so we can just write the k outside of the parentheses. So again, what happened in this step is that we took the x to the fourth, oh, that didn't work, oh, I guess it kind of did, and moved it outside. And then we grouped all of this inside the derivative because these two are just constants, and so they make no difference inside the derivative. And that is how we got from this line to that line. Moving x to the fourth outside and grouping the rest of the interior together so that we could write it to the power of k. Okay, so focusing again on the derivative, I know that d dx of x plus x squared is exactly the same as d dx of x plus d dx of x squared. It doesn't matter if I take the derivative as a polynomial or distribute the derivative to individual terms in the polynomial, I'll get the same answer. In this case, it's just 1 plus 2x. The importance of this is that it doesn't matter if the derivative is inside the summation or outside the summation, I'll get the same answer. So to simplify life, I'm going to move it outside the summation. So the next line, moving the derivative outside the summation, I have x to the fourth, summation, moving the derivative outside, d dx of the summation, k equals 1 to infinity, and then I can simplify this as just negative x over 6 to the k. And now I have the geometric, which means I can take advantage of that a over 1 minus r. So in this case, we'll call this scratch work, we need to simplify the summation. In this case, a is equal to, plugging in just the first term, remember a is always the first term, so plugging in 1, we have negative 1 over 6. R is just the ratio that's being raised to the power, so in this case it is, negative x over 6. We're plugging in the value of 1 for k, negative x over 6. R is the same exact thing, it's just the ratio that's being raised, so in this case it is negative x over 6 again. And we need to simplify the fraction negative x over 6 over 1 minus negative x over 6. That simplifies to negative x over 6 times flipping the bottom and creating a single fraction right here, 6 over 6. We have 6 over 6 plus x. The two 6's will cancel, and we get negative x over 6 plus x. All right, so rewriting the summation, we have equals x to the fourth, the derivative of, I just found what this summation converges to, so I can take out the entire summation and put in the conversions of the summation. Negative x over 6 plus x. And then I just have to find the derivative of this, which unfortunately does mean quotient rule. So I'm going to take the derivative of the numerator, negative 1, times the denominator, 6 plus x, minus the derivative of the denominator, which is just 1, times the numerator, which is negative x, okay, all over 6 plus x squared. And let's see, distributing, I get negative 6 minus x plus x all over 6 plus x squared. All right, and then these two would go away. So that just leaves me with x to the fourth times negative 6 over 6 plus x squared. And simplifying that, I get negative 6 x to the fourth over 6 plus x squared. So summarizing what we've done here, we found what this summation way back up here converged to, and we said it was negative 6 times x to the 4th over 6 plus x squared. We found that by taking advantage of derivatives. So the first thing that we did was try and group all the k's together. We rewrote the x to the k and the k coefficient as a derivative so that we could take away the k coefficient because it was in the way when we were trying to convert this to a geometric. Then we regrouped using the rules of derivatives and exponents to be able to write all of the k's, or the k powers, together in one derivative. And we use the derivative rules again to move the derivative outside the summation, which allows us to use the convergence of the geometric series to replace the series with just a function. After we replace the series with a function, we still have to take care of that derivative that we used. So we use the first derivative and the quotient rule to be able to simplify that away and rewrite just this rational expression. And then we still had that x to the 4th that was following us around the whole time. So we have negative 6 x to the 4th over 6 plus x squared. Hope you find this video useful. Reach out to me on the Hey Professor board or through Pronto or through email if you have any questions. I look forward to hearing from you.